section 6.7, exponential and logarithmic models. In this section, we're going to focus on other ways to more efficiently set up our exponential models. Our special methods for setting up the exponential models is going to depend on the information we're provided about how the substance grows or decays. Our first example of this special information is what we're going to call doubling time. The doubling time of a substance refers to how long it takes for the amount of the substance to double. Let's suppose that Q sub 0 represents the initial amount of a substance, and it has a doubling time of d units of time. Then the amount of the substance Q after t units of time will be Q of t equals Q sub 0 times 2 raised to the t over d. T over d would represent how many periods for which this substance would be able to double. And we're doing 2 raised to that power because since we know the doubling time, to figure out the substance after one period has passed, we would multiply by 2. So if we consider how many times it has the chance to double, we would be multiplying by 2 raised to t over d, the number of times our substance can double. For our first example, the population of bunny rabbits has a doubling time of 3.8 years. I have a room with 10 bunny rabbits. We're going to write a model that represents the population of the bunny rabbits after t years. Since we're provided that the doubling time of the bunny rabbit population is 3.8 years, we can set up our model quickly by using the above formula. Instead of using Q, we'll use P for population. So we'll have P of t equals our initial bunny rabbit population, which is 10. And since we're provided the doubling time, the base of our exponential function will be 2. And the exponent for which 2 is raised to would be t over our doubling time, which is 3.8. Next, we're going to see how long until I'll have 100 bunny rabbits, which means I want my population of bunny rabbits to become 100. So I want to solve the equation 100 equals P of t. Since we already have our model, so I'm trying to solve the equation 100 equals 10 times 2 raised to the t over 3.8. To solve our equation, first divide both sides by 10. Since I can't figure out 2 to what power gives me 10 to try to use the one-to-one property of exponential functions, I do want to use logarithms to help me solve. Because 2 is not 10 or e, I don't want to apply log base 2 to both sides in case I have a calculator that can't handle log base 2. So to make sure that I can use my calculator, I'll apply the natural log to both sides. So on the left-hand side, I have the natural log of 10. On the right-hand side, I can apply the power rule for logs, and I have natural log of 10 equals t over 3.8 natural log of 2. Now to finish solving for t, I would have to divide both sides by the natural log of 2 and multiply both sides by 3.8. That would be the same as multiplying both sides of my equation by 3.8 over the natural log of 2. And I get 3.8 times the natural log of 10 all over the natural log of 2 equals t. And we get approximately 12.6. So it'll take 12.6 years for my bunny rabbit population to reach 100 bunny rabbits. Another special piece of information, specifically for decay problems, is the half-life of a substance, which is often a term that you'll hear a lot when discussing radioactive material. The half-life of a substance refers to how long it takes for the sample to lose half of its initial amount. The exponential model that we can write when we're provided the half-life is very similar to the model that we would write when we were given doubling time. We'll let Q sub 0 be the initial amount of the substance with a half-life of h units of time. Then, the amount of a substance Q after t units of time is Q of t equals Q sub 0 times 0.5 raised to the t over h. T over h would represent how many times our substance would lose half of itself. Because our substance is losing half of its material every h units of time, we're multiplying our initial value by 0.5 raised to the t over h. 0.5 referring to the loss of half of its material, and the t over h calculating how many half-lives are passing over that period of time. In our next problem, substance X has a half-life of 15 years. I have 100 grams of substance X. We're going to start off by writing a model that represents the amount of substance X in grams that I will have left after 2 years. Since I'm told the half-life of substance X, that tells me the quickest way to write my exponential model is by using the version that we have above. We'll have Q be the amount of the substance, so Q of t will equal, first we need our initial amount of substance X, which is 100 grams, and because we're given half-life, our base of our exponential function will be 0.5, and that'll be raised to the t over 15 power, where 15 is our half-life. Now that we have our model, we can answer how long until I have only 15 grams of substance X left, which means I'm trying to solve the equation Q of t equals 15. Q of t we already know is 100 times 0.5 raised to the t over 15. Now that we have our equation, we can go ahead and solve. We'll start off by dividing both sides by 100, and 15 over 100 is exactly 0.15. Here I'll write as a decimal to make the writing more compact, but if the decimal is non-terminating, meaning you would have to round, I would suggest writing a fraction. Now, just like in previous problems, we'll apply the natural log to both sides. That way, on the right-hand side, I can use the power rule of logs, and I have t over 15 times the natural log of 0.5 times the natural log of 0.15. To finish solving, we'll multiply both sides by 15 over the natural log of 0.5, and we get 15 times the natural log of 0.15 over the natural log of 0.5. And when we throw that into the calculator, we get approximately 41.1 years. So it'll take approximately 41.1 years for me to have only 15 grams of substance X left. In previous problems, we wrote exponential models when we were told that the substance would increase by a percentage or decrease by a percentage. In those problems, we would use that information to calculate another point, and then from there we were able to find our base and our initial value to create our model. Here we're going to take a look at a shorter way to set up our model. If we're told that our substance is increasing by a percentage, that percent increase is referred to as a growth rate. And as we know, that would indicate an exponential growth. Suppose a substance increases by a rate r over t units of time. Then the amount of the substance at time t units, which we're going to denote as P of t, can be modeled using P of t equals P sub 0 times 1 plus r raised to the t over t, where P sub 0 we know is the initial amount of the substance. The reason why our base is 1 plus r is the way we would calculate how much substance we gain over that t units of time is we would multiply our initial population by r and then add that to the initial population. Well, if we factor out the initial population, we would be left with P sub 0 times 1 plus r. So effectively, every t units, we would have to multiply by 1 plus r. And our exponent t over t refers to how many opportunities our population has to increase by our rate. Along the same lines, we may be told that our substance decreases by a certain percentage. We will refer to that as a decay rate, and this would indicate an exponential decay. If a substance decays by a rate of r over t units of time, then the amount of the substance at time t units, which we're going to denote P of t, would be P of t equals P sub 0 times 1 minus r raised to the t over t, where P sub 0 is the initial amount. The reason for the 1 minus r as the base is because the way we would calculate how much substance we would have left when we're given the decay rate is we would take our initial amount of substance and subtract our initial substance times the rate. We'll factor out the P sub 0, we would be left with P sub 0 times 1 minus r. So effectively, we're multiplying by 1 minus r each time t units pass. Be very careful, making sure to identify the percent increase versus decrease. In other words, making sure you identify whether we have a growth rate or a decay rate. If it's a growth rate, our base in our model is going to be 1 plus the rate. If it is a decay, the base in our model would be 1 minus our rate. A radioactive substance is decaying into a non-radioactive substance. In 400 days, the substance decreases by 72%. What is the half-life of the substance? First, let's start off by writing our model. Here we're told that the substance decreases by 72%. If we make Q the amount of our substance, the version of our model we're going to use, because we're given a percent decrease, is going to be Q sub 0 times 1 minus r raised to the t over t. From our problem, we know that r is 72%, which is 0.72, and our capital T is 400 days. But they didn't give us the initial amount. So let's write in what we know so far. And we have so far that Q of t equals Q sub 0 times 1 minus 0.72 raised to the t over 400. Do a little cleaning up, and we get Q of t equals Q sub 0 times 0.28 raised to the t over 400. Re-looking at the problem, there is no information that tells us what Q sub 0 should be. So let's take a look at the question and see if it's actually necessary to know what Q sub 0 is. Our question is asking us, what is the half-life of the substance? The half-life of a substance refers to how much time it takes for our initial amount to lose half of itself. In other words, it is the solution to the equation 1/2 Q sub 0 equals Q of t. For our specific situation, we want to solve the equation 1/2 Q sub 0 equals Q sub 0 times 0.28 raised to the t over 400. Notice how we have a Q sub 0 on both sides. Since Q sub 0 is a non-zero value, we can divide both sides by Q sub 0, and they're going to cancel out. And I get 1/2 equals 0.28 raised to the t over 400. So it turns out I didn't need to know what the initial amount of substance I have, because here they canceled out nicely. Now we can solve our equation exactly the same way we did in the previous slides. Apply the natural log to both sides, use the power rule on the right-hand side, and I converted the 1/2 to a decimal. Multiply both sides by 400 and divide both sides by the natural log of 0.28, and we get t equals 400 times the natural log of 0.5 over the natural log of 0.28. And if we throw that into the calculator, we get approximately 217.8 days as the half-life of our substance. A population of II increases 10% every 6 months. How long will it take for the population to triple? Similar to the previous problem, we're given a percentage for which our population will, in this case, increase over a certain period of time. So using P for population, our model is going to be in the form of P of t equals P sub 0 times 1 plus r raised to the t over t. And we have 1 plus r as the base because we have a percent increase. According to the information provided in the problem, r is 0.1 and t is 6 months. But here they did not tell us what the initial population is. So if we just fill in what we know, we have P of t equals P sub 0 times 1 plus 0.1 raised to the t over 6. And if we clean that up, we have P of t equals P sub 0 times 1.1 raised to the t over 6. But again, I still don't know the initial population. So let's check the question to see if I actually need the initial population. The question is asking how long will it take for the population to triple? This means we're trying to solve the equation P of t equals 3 times P sub 0, where the 3P sub 0 would represent the population of our II after it is tripled from the initial value. We already know so far that P of t is P sub 0 times 1.1 raised to the t over 6 power. And if we compare the left-hand side and right-hand side of our equation, notice P sub 0 is a common factor. And since our initial population cannot be 0, we can divide both sides by P sub 0, and we get 1.1 raised to the t over 6 equals 3. So it turns out, again, we didn't need to know what the initial amount of our substance was. Apply the natural log to both sides, just like we did in previous equations. On the left-hand side, we'll use the power rule. And if we multiply both sides by 6 and divide by the natural log of 1.1, we get t equals 6 natural log of 3 divided by natural log of 1.1. Throw that into the calculator, and we get that our population will triple in approximately 69.2 months. Now we're going to revisit continuous growth and decay. Recall that the function f of t equals a e to the rt models either continuous growth if a and r are both positive, or continuous decay if a is greater than 0 and r is less than 0. We saw in previous sections how we can use continuous growth to represent interest compounding continuously. The absolute value of r, recall, refers to the relative rate of growth or decay. If r is positive, we would call it a rate of growth. If it was negative, we would call it a rate of decay. The way we can tell if we are supposed to use a continuous growth model is when we're told that the substance either grows or decays at a rate proportional to its size. Another way to phrase this, the more substance you have, the faster it grows or decays. So whenever we're seeing the phrase the rate is proportional to its size, that is to tell us we're using the AE to the RT model for our exponential growth or decay. Suppose a petri dish of bacteria starts with 200 bacteria and grows proportionally to its size. After 5 hours, there are 800 bacteria. First, we want to know what will the population be after 10 hours. In order to answer our question, first we need to make a model. Since we're told that the growth of our population is proportional to its size, that tells us we're working with a continuous growth model, which means our model is going to be in the form of P of t, P being the population, equals P sub 0 e to the RT. If we take a look at the information they also provide us, we're told that the initial population of our petri dish is 200. So P of 0 will be 200. However, they don't give us the rate. They do tell us that after 5 hours, there's 800 bacteria, meaning P of 5 equals 800. Plugging in our initial population, we have P of t equals 200 e to the RT, and we can use the fact that P of 5 equals 800 to figure out the value of r. Now we need to solve the equation 200 equals e to the 5r equals 800, divide both sides by 200, then apply the natural log to both sides. Fortunately for us, since we're taking the natural log of e to the 5r, e to what power gets us e to the 5r? That would be 5r. So we get that 5r equals natural log of 4, which means r equals the natural log of 4 over 5. Now that we found r, we have our model is P of t equals 200e to the natural log of 4 over 5t. Now we can use this to answer the question. What will be our population after 10 hours? In other words, what is P of 10? So plug 10 into our model, and if we throw that into a calculator, we get that P of 10 equals 3,200. So after 10 hours, we'll have 3,200 bacteria in the petri dish. Next, we want to determine how long it will take for our population to reach 1 million. So in this problem, we want to solve the equation P of t equals 1 million. We already have our model from the previous part, so we need to try to solve the equation 200e to the natural log of 4 over 5t equals 1 million. Divide both sides by 200, apply the natural log of both sides. And because we're taking the natural log of e to a power, natural log of e to that power will just be that power. So we have natural log of 4 over 5t equals natural log of 5,000, and we get t equals 5 times the natural log of 500 over natural log of 4. And if we throw that into the calculator, we get approximately 30.7 hours. Next, we're going to take a look at Newton's law of cooling. Newton's law of cooling is an example of a continuous growth or decay model. The temperature of an object T in surrounding air with temperature T sub S will behave according to the formula P of T equals A e to the KT plus T sub S. In this model, T is the amount of time that the object has been left in the specific surrounding air. A represents the difference between the initial temperature of the object and the surrounding air. So be very careful of A. A is not just the initial temperature. It's the initial temperature of the object minus the temperature of the air. And K is some constant. A hot pocket is taken out of the microwave with an initial temperature of 200 degrees Fahrenheit and left on the counter of the kitchen. The kitchen is 70 degrees Fahrenheit. If the temperature of the hot pocket is 150 degrees Fahrenheit after 15 minutes, what is the temperature after 1 hour? So to answer our question, first we have to start making our model. Because we're dealing with an object being left out to cool, our model will be provided to us from Newton's law of cooling. Now we have to figure out the different parts of our model. A is the difference between the initial temperature of our object and the temperature of the air. Our hot pocket was initially 200 degrees, and the air we know is 70 degrees. So A is going to be 130. T sub S is the temperature of the surrounding air, which is 70 degrees. The only thing we don't know yet is K. So to help us figure out K, let's at least plug in what we know so far. So we know so far that T of T equals 130 e raised to the KT plus 70. From our question, we know that after 15 minutes, our hot pocket is 150 degrees. In other words, T of 15 equals 150. So if we plug that information into what we know about our model so far, we have to solve the equation 150 equals 130 e to the 15k plus 70. Now we'll isolate the e to the 15k, and we have 8 over 13 equals e to the 15k. Apply the natural log to both sides, and we have natural log of 8 over 13 equals 15k. And after we divide by 15, we get that our constant k is the natural log of 8 over 13 divided by 15. Now that we know k, we have completed our model, and we get that our model T of T equals 130e raised to the natural log of 8 over 13, all divided by 15, times T plus 70. Now that we know our model, let's answer our question. First, what is the temperature after 1 hour? Now we have to be very careful with units here. As we did our calculations for K, we worked with our time being in minutes. Since we're trying to figure out what our temperature will be after 1 hour, we want to convert 1 hour to minutes. So we know that there are 60 minutes in 1 hour, so T would equal 60 to represent 1 hour. So we're trying to evaluate T of 60. Plug 60 in for T into our model and use a calculator to evaluate. We get approximately 88.6 degrees Fahrenheit. Next, we want to know when will the hot pocket cool to 100 degrees Fahrenheit, which means we're trying to solve the equation T of T equals 100. We already know what our model is from the first part of the question, so we're trying to solve the equation 130 times e raised to the natural log of 8 over 13 all over 15 times t plus 7 equals 100. We'll solve this equation very similar to the way we found k in the previous problem. We'll start off by isolating e to our power. So after subtracting 70 from both sides and dividing by 130, we get that e natural log of 8 over 13 all over 15t equals 3 over 13. Now we'll apply the natural log to both sides. We get that the natural log of 8 over 13 all over 15t equals the natural log of 3 over 13. So after multiplying both sides by 15 and dividing by the natural log of 8/13, we get that t equals 15 times the natural log of 3 over 13 divided by the natural log of 8 over 13. And if we throw that into the calculator, we get approximately 45.3 minutes.